In 2013, Calgary was devastated by a massive flood which forced the displacement of over 100,000 people and resulted in over $5 billion of damage. The ability to predict the areas that will be most impacted by future flood events would allow planners and officials to proactively work to mitigate the worst of the damages. Using data on which areas of Calgary were inundated, we can create a model that measures the effect of different spatial variables on flood inundation. This is done in 4 key steps. First, separating the data in half and testing the explanatory power of different spatial variables on actual inundation. Second, testing or cross-validating our model based on the remaining half of the Calgary dataset to see how well the model predicts on the other half of the data. Third, spatially cross-validating our data to see how well the model performs on areas with different spatial features. Finally, applying our validated model to a similar geography to predict future flood events in other cities. First, we examined 10 spatial variables that may have had an effect on flood inundation. By analyzing each variable's significance with respect to inundation and employing the backward and forward selection techniques, we arrived at a final model with 6 variables. These included within 150 meters of water, road density, distance to developed land, distance to steep slopes. Areas closer to water are more likely to be inundated. Here, we defined close to water as within 150 meters, shown in yellow. Areas with a high density of roads leave smaller pockets of pervious surfaces to absorb stormwater. Developed land has high levels of impervious surfaces which can increase runoff to surrounding areas. Steep slopes can increase the speed and rate at which water flows and pool water in certain areas. Using these significant factors, we predicted inundation for the other half of the Calgary dataset, comparing our predictions to the actuals. Our model predicted the probability of inundation in each area of the city, as seen here, from low probability, shown in green, to high probability, shown in blue. Assuming that a probability over 0.5 is associated with inundation, we can map our predictions for which areas of Calgary will or will not flood. Comparing this to the actual inundation throughout the city, we can visualize our model's success at predicting inundation. A quality model is determined by goodness of fit measures as well as its generalizability to other areas. These can be understood by looking at our model's accuracy. This model correctly predicted whether 94% of land area in Calgary would flood. This model correctly predicted 68% of inundated areas. This model looks good for predicting flooding across all of Calgary, but does it have equal accuracy across areas and neighborhoods that have different spatial features? Beginning with our full data set and this time separating out a train and test set geographically, we can measure our model's success on 2 sample neighborhoods, one in a highly developed area, shown here in yellow, and one in a more open, less developed area, shown here in red. Our model predicted inundation, shown in blue, for the highly developed downtown neighborhood. This compares well to the actual inundation on the right, but suggests that our model may be overfit for this neighborhood. For the less developed neighborhood with more open space, our model does not predict inundation as well, suggesting that it may be underfit for areas with less development. This is likely due to the number of development-related variables used in the model. The value of a model is in its ability to be applied to other similar geographies to predict future flooding. We applied our model to Austin, a city similar in land and water area, to see where it predicted flooding based on the same spatial variables considered in Calgary. Our model predicted the probability of inundation across Austin as seen here, from low probability, shown in green, to high probability, shown in blue. We think this prediction is fairly accurate for developed areas along the water, but may be under-predicting flood inundation in certain less developed areas since our model relies on a number of development indicators to predict flooding. Planners and government officials should be sure to take the model limitations into account when planning flood mitigation efforts.